Alright, ladies and gentlemen, in this video what we're going to do is continue the question where we left it off from part A. So this is the question here, as you can see. Okay, so what we have here is a question B here, which is telling us to find the work done by the force field in moving the particle from A to B. Okay, so once the work done by the force field in moving the particle from A to B, so from point A to point B. Alright, let's look at the solution and see how it is done. So when you look at this, okay, so this is part B. We use the formula for F dot V dt. Okay, we use the formula here for F dot V dt. Remember, this was one of the formulas for getting the work done. And yes, why we're using this formula is because of what we've been given. What we've been given only allows us to use the formula of F dot V dt for the integral of F dot V dt. That's the only formula we can apply here. Okay, we can't apply the formula for the integral of F dot dr in this case. It won't work. You'll see why. Okay, so now using the formula for work equals the integral of F dot V dt, we know that at point A Wt is equal to 0, right? Rather, omega t is 0, hence Ta is equal to 0, right? If omega t is 0, and then from here you make t the subject of the formula, you cancel this omega with this 0 and you remain with t equals 0, mean Ta equals 0, mean time at A is 0. And then at point B, omega t is just pi over 2. Okay, and in case you're wondering what omega t is, it's just this angle here is omega t. Now we're saying at point B it is just pi over 2 because the particle has moved an angle of 90 degrees, which is pi over 2. Okay, so what are we saying? If omega t is pi over 2, if we make t the subject of the formula here, we'll get t equals pi over 2 omega, right? We'll get t equals pi over 2 omega, which is the time at B. Now using this formula, we're going to now start solving for the work. So now when you look at our question, we don't have the force, right? We don't have the force, but this V, we've calculated it from the previous question, which is part A. V, we know the velocity. The only thing we don't know now is force, and we know the formula for force is ma. Force is just the mass times the acceleration. So now, since we already know V, from V we can calculate acceleration by differentiating V, right? V, this V is solved here. We can differentiate it with respect to time to get acceleration A. So this is what we do. Force equals ma, which is m dv over dt, which is m d over dt over this V. Differentiating this whole thing inside these parentheses, we'll get this expression with the m outside. So this is in other words the acceleration here. Okay, and then factoring out negative m omega squared, as you can see here and here, m omega squared is common. We can factor it out and get minus m omega squared and leave a cos omega t I plus b sin omega t j inside the brackets. Alright, and from here we can say omega or rather work is equal to, remember the formula, F dot V. So now the limits of integration are from 0 to pi over 2, since pi over 2 is just the time at B, from 0 to pi over 2. And this is our F here. This whole expression is our F, which we just found here, dot this expression, which is our V, okay, which we already know. So dotting this and this, we know how to do dot product, all of us. You just take the terms in I, dot them with the terms in I on the next part. The terms in J, we dot them with the other terms in J on the other part. So dotting these, we get this expression. After getting this expression, we can even factor out m omega cubed, since m omega cubed is common. When we factor out in this expression m omega cubed, we remain with a squared minus b squared inside the brackets, sin omega t cos omega t. Alright, and work will be equal to half m omega cubed. Okay, now let me just explain what has happened here. I know some of you would be confused what has just happened here. Here what we've just done is, we saw that this sin omega t and cos omega t has got the potential to become an identity, right? This can be used as an identity if it had a 2 in front of it. Sin omega t cos omega t, this expression can be used as an identity if it had a 2 in front of it. So when we introduce a 2 here in front, we have to introduce a half outside so that they cancel each other and we return to the original expression. So we've put a 2 there and a half outside. Okay, remember here we've just factored out all the constants. These are the constants. We factored them out and introduce a half in front, and here we introduce a 2 so that when they cancel they get the original expression. So we found this identity here. This is an identity. So now if this is an identity, right, rather this is an identity which gives this sin 2 omega t. This identity is equal to this, and these constants return as they are. The limits run from 0 to pi over 2 omega as usual, with respect to dt. With respect to dt there. So the work is equal to half m omega cubed a squared minus b squared, square brackets, minus 1 over 2 omega cos 2 omega t pi over 2 omega. Alright, so that's what we get after integrating this expression. We get this. Okay, so then from here we substitute back these values in this expression, and 0 inside, we'll get something like that, minus cos 0. We'll get this expression and that expression, and finally this expression. So this is our work done, which is half m omega squared a squared minus b squared. Alright, so that is our work done. And part C here is saying show that the energy principle is obeyed. The energy principle is just the principle which shows that work done is equal to change in kinetic energy. I'll repeat, when you hear something like show that the energy principle is obeyed, then just know that they are asking you to show that work done is equal to change in kinetic energy. And when you look at this expression for the part C here, we know that work is equal to change in kinetic energy. That's what we need to show. We need to show that this is true. And we know that work is equal to half mv kinetic energy is just half mv squared. So the change would be kinetic energy final, which is at B, this expression, minus kinetic energy initial, which is at A, this expression, because kinetic energy is always given by half mv squared. And the work would just be half m open brackets omega squared a squared minus omega squared b squared. Kinetic energy at point A, we found it here in the first part. You remember this part. Kinetic energy at A was this, kinetic energy at B was this expression. So you just have to take this expression minus this expression, then you found your answer, as it's been done here. Have you seen what we're getting? This expression here. Taking the difference gives us half m omega squared a squared minus b squared, which is just equal to the work we found in B. So this work is equal to this work. Hence we have proved that the energy principle is obeyed. This is equal to that. Now let's look at part C. Part C is just showing that show that the work done in moving the particle once around the circle and once around the ellipse is 0. That's what they want us to show. Show that the work done in moving the particle once around the ellipse is 0. And here we're going to see in the solutions here, show that the work done in moving the particle once around the circle is 0. So the particle is starting from this base line here, going all the way up to that point, right? So starting from 0 degrees, going all the way up to 360 degrees. That's the only way we'll move once around the circle. We have to go all this way up to there, and for us to move this path we have to go 360 degrees, which is equal to 2 pi. So the limits of integration for this part, this other part will be 0 to 2 pi. We just say omega t is equal to 2 pi once it has gone around the ellipse. Let's look at the answer. As you can see, we are back here. We're saying that this time at final point of the particle omega t is equal to 2 pi. This time at final point of the particle omega t is equal to 2 pi, you see. And when we make t the subject to the formula, we will get 2 pi over omega. So using the formula 0 to 2 pi over omega of f dot v dt, we substitute back what we have. We know force, we know v. So getting the dot product, we got it already in part B. We got the dot product, and the dot product was just this expression in brackets here. This expression was our dot product. So we just pick up from here as we got it, or rather, sorry, the dot product wasn't that. The dot product was what we got after taking this force and this force. We got this as the dot product, which is this expression here, okay, which is this expression, which is the same as this expression. Alright, so when you look at our solution for D, we've got that same expression we found previously for dot product. We've just plugged it in straight there, which is this, and then factoring out the constants, we get this expression. And we've put a half here outside because we want to multiply this, sin omega t cos omega t by 2, so that it becomes an identity. Hence we multiply by half the outside. so that they can cancel out, and we return to this. So now this again is an identity. We follow the same procedure we did, which is sine 2 omega t, integrating it, you get this expression, plugging back the values and simplifying all the way here, you get 0. You will get 0 finally. And that's how we do it. That's how it is done. Alright, yeah, we shall see you in the next session, and stay tuned.